2020 учебном году. Докладчиком будет Риджу Басак. Доклад будет называться «Осцилляторные мультипликаторные оценки возле L1». Okay, today is our speaker Riju Basak from Taiwan, and the talk is oscillatory multiplier estimates near L1. Riju, please.
Okay, thanks, and thank you for giving me the opportunity to present my work here, and thank you, Professor Dima, for inviting me to come here. This is the first time in Russia, so far it's good. So, okay. So today I'll talk about oscillatory multiplier estimates, and we'll also talk about some applications of this oscillatory multiplier estimates on wave equation, and this is how actually this type of multipliers, the origin of the multipliers come from. So the talk of my title is oscillatory multiplier estimates near L1. So we'll mostly talk about the estimates near L1. Okay. Am I audible? Is it okay? Okay. So I will come to the definition of what type of multiplier I am going to talk about. So before that, let's try to motivate. So what type of problem we want to study. So for that, we start with a Cauchy problem for wave equation. So consider the Cauchy problem for the wave equation. So the wave equation is given by, so u is a function on Rn, so x comma t is coming from Rn cross 0 infinity, and the wave equation is given by, so in double derivative with respect to the time variable t and is a Laplacian with respect to x, and we have the initial condition given by f x, and there are two initial conditions. One is x u at t equal to 0 and derivative of u, so t at 0, and is given by g. So this is the Cauchy problem for wave equation. And this is if you assume let us say f and g are very nice class of function, then one can write the solution very explicitly. In particular, if you the solution is given by this. Two pi mod psi t. So here this f hat means the Fourier transform of f at xi. So I will write at least for definition the, so f hat xi is integration of f by Rn integration with respect to this exponential 2 pi I. Okay, I think it is not visible. So it is on the right. Okay. So I am writing here. So f hat xi is the Fourier transform of f at xi. So it is defined by two pi I x dot xi, and this dot is usual linear product on Rn. So, we write the solution of this equation with respect to this. So, one term with cosine and another term with sine. So, an integration over R n and here also integration for R n. And actually one can check if you let us say if you assume this is well defined. So, this integral is finite, then one can check this is this u x t given by this two integral actually solve this equation. And this can be easily checked using if you take the Fourier transform in the x variable and then it's convert to OD, and if you solve the OD then you can actually write in this form. So, if you see this two integral, this is actually the Fourier multiplier operator. This type of integral is called the Fourier multiplier operator, and this function is called the multiplier. And if you see this multiplier, this means cos and sine. So, one can write cosine and sine in terms of the exponential, and this problem actually then reduced to this problem. So, we write, if you write cos and sine in terms of exponential, so then one can reduce to this. This and we call this LT of fx. In some sense, it is actually because we write cos in some cos and sine in terms of this exponential. So, to study the solution of wave equation, it is equivalent to study this operator, right. And also one can check using some of the property of the Fourier transform, that means the L2 norm is preserved by the Fourier transform. This is called also the Plancherel formula. If we use this formula, then one can show that the solution and also this operator is bounded on L2 to L2. So, this is an easy application of Plancherel, that this operator maps for of course, we are taking the fixed t, and similarly for if you have this, then you also can have this for this is the same for this solution. Now, the question is that if you want to study the regularity of u for a fixed time t in the variable x for other Lebesgue spaces, so question is that is this basically is what is the condition one can actually impose this initial condition, so that this operator Tt is bounded on LP to LP or LP to LQ. So, that is the main question that we are going to talk about in this talk. But if you go like for other p, we cannot expect this gives you the LP to LP solution. We need some regularity here. So, regularity means we want to have regularity in terms of Sobolev space. So, to capture this regularity, we introduce a factor here. So, maybe you can write it here. One plus square t j square b by 2. So, this is the inverse power of 1 plus Laplacian, right, 1 plus t Laplacian. of course with this power. And this actually, this factor f with this actually captures the how much Sobolev regularity we need to have the operators is bounded on LP to LP. And that is what we are actually going to talk about, like what is the optimal B one can choose, so that this maps is. So the question that we are asking is, what is the optimal B required such that okay, because we are introducing here B, so we also here write the operator depending on B. So this is TBT. So now this is T bounded on LP Rn to LQ Rn. And question, so answer of this question actually already known. So what is known, that is I have to write. So answer is, so when you have LPRN to LPRN, if and only if we need B has to be bigger than equal to n plus n by P minus 1 by Q minus n minus 1 by 2.
So where is Q from LP to Q? Right?
Oh, sorry. Yeah, thanks. This is LP to LQ. Yeah. So and this is true when P and Q strictly bigger than 1. But also one can talk about for P equal to 1, but in this case we need some slightly bigger regularity here. So for P equal to 1, and only if B is strictly bigger than, if you put P equal to 1, this is actually n plus 1 by 2 minus 1 by Q. And of course, if you want to have result with that boundary point B equal to, then if you replace B L1 by Hardy space, then one can have this estimate. So that means if you replace the L1 by Hardy space, so then we can go with this equality part. And all this result was due to Miyachi and Perel, and both actually are independent work, but all these results actually one can see from these two papers. And also actually there are some study before this to work, but the sharp range of this B, so that this is happened is due to this these two mathematicians. And actually this paper appeared in the same year, but two different papers. Okay. Now we focus into these two estimates, this L1 estimate and the Hardy space estimates. So what is Hardy space? So it is, so Hardy space is subset of L1 with extra property. So what is the extra property? So if f is in Hardy space, then the integration of f over the support of f is 0. And also the member of Hardy space also have some good properties, means the member of Hardy space can be decomposed into some nice class of function which is called atoms, and that is what actually when you estimate operator on Hardy space, that type of property is actually needed, usually people used to prove this type of estimates. Okay. Now, you focus these two estimates, difference between two estimates only this boundary point, and this type of actually appeared in the estimate of this type of appeared in many places, and what our question here try to improve these estimates, these Hardy space estimates. So, what is meant by the improvement here? So, if you see here from H1 to L1, the difference is the epsilon, means if you choose slightly epsilon regularity, we get the L1. So, the improvement means we want to find some space W which contain H1 and which also contain in L1, such that if you, let us say, if you have estimate of this from W to LQ and with the same regularity as the Hardy space. That means, if we choose B is bigger than equal to if you use the same regularity of Hardy space, and but we choose some space which is lie between H1 and L1, and that is what we are going to actually estimate. So, that and this gives you actually the improvement of Hardy space estimate. But now we have to see what is the space here, that we have to see first, but before that actually this type of problem, like the improve of L1 estimate with respect to some with respect to some subspace of L1 has been studied for many different operator and different problems. And one of the problems that's related to this work is the Sobolev embedding on this near this space L1. That means we are going to talk about some estimate near L1 for risk potential. So, what is this potential? So, risk potential is defined by, so let us take the parameter alpha belongs to 0 to n, then so risk potential, which is denoted by I alpha of order alpha, is given by so we have some normalization constant, then we integrate over this kernel x minus y to the power n minus alpha dy. And for the risk potential, we know that this maps H1 to this LQ space, that is n by n minus alpha, but it does not map L1 to this space. Sorry. And if you compare these two with that estimate between L1, it is in this similar flavor. But as I said, people have studied what type of subspace of L1 one can consider, so that it I alpha maps that space to this space. So, this problem has studied for many years and by many mathematicians. So, but the problem that is studied mostly in the vector value setting. So, that means the function is actually a vector valued function. In this direction, so there are lots of contribution, like I should write some names. So, one of the few are important contribution are by Burgen, Bregis, Stein, Magia, Schaftingen, and this by Hernandez, Spector, and also by Professor Dimitri Stoliarov. So, basically they found some appropriate subspace of L1. So, so that this maps it also contain Hardy space, and this map that space to this space, and this is the kind of improvement of the L1 estimates. I am not talking about actually the spaces here, but I am definitely talking about some space that is connected to our problem. Recently, as I mentioned, this all these results are for vector valued setting, but recently Spector and Stoliarov, they define a space which capture this scalar value of the function, and also which is actually a space which is also subset of L1 and also capture the scalar value nature of the function and satisfy this type of Sobolev inequality. That means that space to L1. So, this space they call ds beta, they denote by this space, and also this space is called the space of dimension stable space of measures. So, this space they call this name because they satisfy some kind of dimension stability estimate, and this space is also contain H1 and also contained in the space of finite hadron measure on Rn. And this space also satisfy this type of Sobolev inequality. That means I alpha map ds beta to L n by n minus alpha. Okay. So, that is actually this is the space for our case also. So, we also have similar estimates for this space. So, to define our result or to state our result, sorry, first I need to define what is this space. So, what is this space? To define this space, okay. To define this space, we have to define what is called the beta atom. So, beta atom is a a measure. So, A belongs to space of all finite resonant measure MBRN is called beta atom. Here beta is belongs to 0 to n if there exists a cube Q set of Rn such that support of this measure inside Q and A on Q is 0. Third is this type of Bezoar space condition is satisfies. So, supreme over T bigger than 0, T to the power n minus eta by 2 Pt convolution A L infinity norm is less than equal to 1 by length of Q to the power beta. So, and Pt is the heat kernel. So, where Pt of x is x square by 4t by 2 t n by 2, and we also have the total variation of the measure q is less than equal to 1. So, if the measure satisfies this 4 condition, we call is a beta atom, and it is to know the Hardy space, the atom of the Hardy space, this is also similar condition satisfied except these 3. So, in Hardy space we have instead of the Bezoar space we have the L infinity or some LP condition here. Okay. If you have this beta atom, then we define this space ds beta. So, the collection of all finite element measure such that mu can be written as a lim sup of lambda IL AIL I from into L and AILs are beta atoms and okay, sorry, this limit in the sense of Wichita, basically this convergent means that actually this is converging the Wichita topology of the measure, and also going to infinity I from 1 to L lambda IL, this is finite. So, this ds beta space are collection of all finite element measures such that we can write mu in terms of these atoms, beta atoms. And the example from what this type of spaces are that I. So, if you take measure mu, sorry, which is finite resonant measure from Rn to Rn, and if you consider the divergence of mu is 0, then each component phi I is actually belongs to ds 1. And for other beta, one can construct using some more complicated examples. Okay. So, let us talk about some properties of these spaces. Yeah.
This example is a quite complicated theorem by Hernandez and Steffen.
Right.
You can decompose any divergent measure as these tricky atoms. This where the definition came from the tricky field. By the way, based on Smirnov's decomposition of this type of charge.
Yeah.
Sorry.
Yeah. Thanks. So, the properties, one of the important properties is that, so when beta equal to n, so ds n is coincide with the Hardy space. And also they satisfy nested properties like this. So, if you choose let us say beta 1 less than equal to beta 2, then ds beta 2 sorry ds beta 1 is bigger than ds beta 2. Okay. So, that means this is and this is the smallest space is this H1, and if you beta is smaller, then this space increase and it is going towards the space of finite resonant measures. Okay. So, this is our actually space that is we are also considering here, and inspired from this result by Spector and Stoliarov for the result of Riesz potential on these spaces. Let us write our results. So, where should I write? So, this I think I can erase this part, or no, this I should not erase. So, I think I can erase this part. Our result actually divide into few parts depend on the which range of Q we are in. So, the first result is so in this in the first theorem we are in this range. So, let Q belongs to 2 to infinity, and in this case we also assume that beta the full range 0 to n, and in this case we also assume our regularities as in the Hardy space n plus 1 2 n is this. Now, if you for these parameters, so we have this estimate. So, then there exists a constant C which is depend on dimension in the beta and also Q, such that T of B mu L Q is less than constant ds beta, and this constant actually also depend on T. Actually, I can explicitly calculate. So, this is n by p prime. So, this is the first result which is in this direction, but if you take Q is smaller than 2, means between 1 to 2, then we have a restriction on beta. So, the second result is, but this result also divided in two parts, means from dimension 3 onwards we have different range of beta, and when you have dimension 2 we have different range of beta. So anyway, so basically all these estimates actually were taking n bigger than equal to 2, because in dimension 1 things are getting the result to prove this estimate is quite easier. So let q this, and in this case we are okay. We want to divide it into two parts. So first is the first part is dimension n bigger than equal to 3. This is, and in this part we take sorry, actually first we write this one, because in this case this q is anyway this. The first one is n when n is bigger than equal to 3, and in this case beta we are choosing from n minus 1 to n. Then we have similar result. So then T T be mu L Q is then equal to constant time n by p prime. Okay, this p prime basically the Holder conjugate. So p by p prime equal to 1, and this is mu T S beta.
So if the first theorem do in Q coincide, can find p that is power of t.
Sorry.
I cannot find the parameter p.
Oh, sorry. You are right. Actually, it's my mistake. So it should be q. Yeah, thanks. This is this results for dimension 3, but for dimension 2, similar result, but again some restriction for dimension 2. So beta here is more restrictive, it depends on p. So sorry, means q. 2 by q to 2. And okay, then we have similar result. Then so this restriction actually is looks it's not actually restriction, is actually it is expected to be actually the end point, this beta n equal to n minus 1. But we don't have a counter example, explicit counter example, but one can expect this beta equal to n minus 1 might be the end point. So this is because of the nature of this type of multiplier operator. So why I am saying so, because this multiplier operator, so let us talk about this thing. So this multiplier operator T B, so this is because it is a multiplier operator, we can write it as a convolution operator. And the this is the kernel, and the singularity of the kernel actually lies on this cone. If you are talking about the space time together, so but for a fixed time t, it is lies in this sphere of radius t. And for fixed time, because the singularity lies on the sphere and it is a n minus 1 dimensional object. So if you are taking here beta is strictly less than n minus 1, that means your measure is supported on some lower dimensional things, it can be blow up when we are in the higher dimension like n minus 1 or more. So that's why it is kind of expected that it should be the end point, this part, but we don't have, unfortunately we don't have the counter example for this. So for this, but for dimension 2, it can be expected to be can be improved. So it is not because here if you dimension 2 it should be 1 to 2, but if like it is not like that, because if you q is close to 1, it is actually close to 2. That means there is some improvement one can make here. But this of course this restriction is coming because the artifact of our proof, how we use the estimates. Okay. And let us discuss the proof of these theorems. Okay. Let us talk about the first theorem, where we get the whole range of beta, and in this case we prove these estimates, theorem 1, using complex interpolation techniques. But to use complex interpolation, we need at least 2 estimates to interpolate 2 estimates. So that's I am going to write here. Let's see just this one. Let's talk about the proof. So proof. Yeah. This is okay. Let's put the name. So this is joint work with my postdoc mentor Daniel Spector, and it is still submitted in journal. It's a recent work. So maybe 2025 December we submitted some, and also you can find in archive. This one. So proof of theorem 1. To prove this theorem 1, we use these 2 estimates. So we take b equal to n by 2, and we have some L2 estimate here. So this is the L2 estimate, one endpoint. The another endpoint we have some BMO estimate. So for this we choose this parameter is n plus 1 by 2, and for this we have BMO estimates. Okay, so we have some constant here. Actually, I don't write t here, so one can actually prove the estimate for t equal to 1, and then using dilation argument and the property of the Fourier transform, one can actually get the estimate for all t. Okay. So it is actually sufficient to prove for t equal to 1. And okay, this we actually prove these 2 estimates, and if you have these estimates, then if you use some complex interpolation techniques for this endpoint spaces with this L2, one can actually get the estimate for between q to infinity. And actually complex, these with complex interpolation gives theorem 1. Okay. So, how to prove these estimates? This L2 estimate, we use the estimate from the paper of Spector and Storiaro of the Risch potential. So, how we actually use their results? So, let us write. This can be observed actually easily using Plancherel. So, T by 2 mu L2, if you take L2 square by Plancherel. So, this is less than equal to, we are taking n by 2, okay, up to some constant. So, there should be some constant. So, this is minus n mu hat chi design, and this basically if you use Plancherel and use the definition, we can get this. And now, this is again right in terms of up to some constant, again using Plancherel. So, the L2 norm of the Risch potential. And now, if I use the estimate from paper of Spector and Storiaro, so we can have mu ds beta square. This is exactly how if we put alpha, that is how the range n by n minus alpha actually, this is actually 2. And this is of course follows from the paper of Spector. And this is the L2 estimate we need to we actually need. And for this estimate, we use the property that ds beta is in L1, and because it is in L1, sorry, is subset of L1. So, actually it is sufficient to prove this estimate for this, or maybe we can write this is not L1. So, maybe space of finite random measure. So, we have this, and this is actually we actually able to prove using the classical results of Miyachi's and Perel estimate, this estimate. And if you use this, then actually complex interpolations gives you the estimate for this, and this proves the theorem 1. And for theorem 2, when we are in this range, we need to we need couple of result, and for basically the kernel of this operator. So, we need to have some estimate on the kernel of this operator. And here we use, of course, here it is implicit that here this we are using this in coming from these spaces ds beta. This is already done in this paper, we just use this, but in this result, like when we are in Q between 1 to 2, we are again using these two property of the beta atoms very frequently. And to prove this result, we first deduce our problem into like for similar operator actually. So one can write this operator TBFX into sum of two operators. So I will define what is that. So this is TB of mu there is a measure nu b depend on b convolution with another operator t tilde b mu of x. So we decompose our operator TB into these two pieces. So what is this operator? So let us take a function psi, which is psi is C infinity function, and which is 0 near origin, let us say b 0 comma 1, and psi is 1 on 0 comma 2. So that means we have this one, and after this one, sorry, it's not bad. So this is in 0 1, and outside after this is 1. And if you define using this function, we define these operators. So what is T bar B? So T bar B of x is psi xi 2 pi xi minus b to the power I xi and mu hat xi to the power this one. So if you see, we just introduce this factor the original operator t, and t tilde b is just the complement of this actually. And see, in our original operator we have 1 plus, but here we are not taking 1 plus. To compensate this, we actually this is we need this measure. And what is this measure? So this is a finite element measure such that the Fourier transform of mu hat is this 2 pi mod xi b 1 plus 4 pi square mod xi square b by 2. This is the ratio of this number and that 1 plus mod xi square that appeared in the original operator TB. And one can prove that basically this is a finite element measure. And because of that, this operator is very nice. So this operator actually yeah. Right. So this operator, the kernel of this operator actually very nice, and they are integrable kernel, and this maps L1 to LP. any LP, actually any LP to LP, LP to LQ. And because this is a, that's why one can actually, because it's a very nice operator, one can actually exclude this operator, because this operator already satisfied our estimate, because this is a very nice operator. And because this is a finite resolution measure, so this convolution with this measure with this operator also preserve the LP norm, and that means we only need to actually estimate this one. Sorry, let me check. Oh, sorry. Actually, it's my mistake. So this is this is T tilde and this is T bar. Sorry, this is 1 minus psi basically is the compactly supported part. Okay, right. So this is actually, sorry, this is the operator where behaves very nicely. This is a compactly supported multipliers, and this operator are this T tilde. That is what we are going to talk about. So now all those things reduced to this operator. Why are doing so? Because this the kernel of this operator is actually studied by Miyachi, and this the kernel estimate is actually explicitly known for this operator. So that's why we reduce this operator, the estimate of this for this operator. Okay. Now we will forget about this thing, only we will consider this operator. So what is known for the kernel estimates? Let's so this is our now operator. So T tilde B of x, we can write again some convolution kernel K tilde mu x, and the known property is that we have actually some asymptotic point of estimates, that is the derivative of this kernel. So we are taking alpha derivative. So this is less than equal to, after some constant, 1 minus mod x to the power b. So b is b minus n plus 1 by 2 and minus alpha. Yeah. And okay, this is true if we are near to 1. So that means near 1. So this kernel is actually a singularity. Means near 1 means I am saying when mod x is equal to 1. That means in this sphere. And if you are away from the sphere, after some constant we have very large decay. Means n is whatever you choose whenever mod x is going to infinity. That is why actually this singularity actually appeared. So this kernel estimate we need when we are talking about smaller atoms, and for larger atom we again need to decompose this operator using we decompose actually in the frequency side using dyadic partition of unity. Let us talk about this. Okay. So this part is done. I can erase this part. So as we are in ds beta space, by standard argument, one can actually reduce to this estimate that this T tilde of B acting on A, and if you take LP norm, it should be A is basically, if you take any beta atoms, so A is beta atom, and if it is uniformly in with respect to A, C is independent of A. So, this is sufficient to have estimate on ds beta spaces. So, it is sufficient to prove for beta atoms. Now, we divide into two parts. The case 1, when let us talk about small atoms first. So, we choose this some constant because it is because of our convenience. So, we choose LQ is less than equal to this number, means when basically. So, LQ is basically what is LQ? So, Q is where the support of A is. So, support of A inside Q. So, when we are talking about the smaller atoms, we will use this estimate that I have written. So, how we use? So, for this let us write T beta of A. So, this is convolution operator. So, we can write y, and now we will use the cancellation property of the atom. So, we write Kb, what do you write? Kb tilde, sorry, this should be tilde, this is tilde, because this is 0 on the support of Q, this is also Q, these are same. Now, if I take these two together, so this is now, if I use mean value theorem here, so we can write mod Q 0 to 1 x minus s y, this is okay, this is the gradient times y ds a y dy. Sorry. Okay. Now, if I take modulus here, then one can take more inside, and finally, we have this estimate. So, T tilde of B of A of x is less than equal to integration over Q 0 to 1 gradient of x minus y mod y sub a y dy and ds. Now, because it is in the cube y, so this is dominated by length of q times one can take the supremum of this and the L1 norm of A, and which is actually bounded by 1. So, this is basically you can remove. So, this is what we get. Now, we have to estimate the this LQ norm of this operator. So, now I use this estimate. So, here one have to see that these estimates actually behaves wherever x is lies, like behaves accordingly. So, if x minus y is near sphere, then it behaves like this, otherwise it have nice decay. So, for that we will divide our range into few species, so that it behaves accordingly. Basically what we will do, so it is inside the circle, should chalk. So, singularity, it is inside, singularity is inside the circle. So, we will divide the region into few parts. So, first we will take some portion here, and then another portion which is outside, and the remaining is this part, this annulus part, where we have the singularity. So, we will divide accordingly. So, how we will divide? So, let us write. So, if we are taking this LP norm, or LQ norm. So, we will divide into 4 parts. So, let us write this AIs. So, what is actually we need 4 parts. So, what is AIs? So, this sets, first of all, what is A1? So, A1 we are collection of those x such that mod x is less than 1 minus this number. So, again we are choosing this is for our convenience, this number, but important thing is that this number is actually where the inside part, this part. The second A2 is where we are in the annulus. So, that means 1 minus this one, 1 plus this. So, that is means we are in this annulus. So, where the singularity is in, and this can be very small, very like thin, depend on if your LQ is very small. Anyway, you are in this range, so it can be very thin. And other two are basically the outside part, because we are very thin, we want to actually estimate decompose in another region which is slightly bigger than this, but but its singularity of this means this boundary when LQ small, it can be very close. So, that is why it depends on these estimates. So, and the remaining one is just a complement. So, the A3 is basically this number less than mod x less than equal to 2 square root n. Or maybe I choose LQ3, I think it's fine. So, this A3 and basically A4 is the complement part, Rn minus union of AI, I equal to 1, 2, 3. And for the estimate, we if you use this estimate, this is actually because in this estimate what happens. So, because we are in this range, if let us say LQ is very small, it can be close to this number, then basically we are in this range. So, if we use this estimate, then exactly we will actually get okay, let us write. So, what we will get for at least for A1, because estimate for A1, A2, sorry A1 and A3 are same, and A4 we have very nice estimate because of this decay, but the important estimate for A2 where we have the singularity. So, at least we will write for A1 now we will use this estimate that we have done here, this one. So, if I use, so this is less than equal to length of q to the power q A1, and now if I use this estimate and also if I use y is in AQ, so we can write in terms of this mod x. Basically, this is A1 means mod x less than 1 minus 2 on LQ, and this is and now in our case okay, actually we will estimate. So, if you remember, so what is our assumption on B? So, B is bigger than this number, right, this number, and here if you put basically what we need, we only need to estimate for the boundary, mean boundary may be equal to part. If B is strictly bigger than this, we already mentioned that this when B is strictly bigger than, then this is actually map L1 to LQ. So, that means it is a better estimate. So, we do not need to consider for strictly, but only important part is equal to. If you put equal to part here, these estimates what we will get. So, n by 2 n will cancel. So, this is basically minus 1 by q, because here alpha is 1 because we have the gradient, minus 1, and we have power q because we are taking LQ. So, if in this case it is actually minus 1 minus q. And okay, so if you see here, what is 1 minus x? 1 minus mod x. 1 minus mod x is bigger than this number, and this is how exactly where it can be integrable, because it is bigger than basically this is minus 1 minus q, and if you use that, then exactly we will get basically LQ to the power minus q, and this will cancel, we will get 1. Of course, this is some constant. That is what actually we need to prove. We need to prove here this is C independent of Q, and similar estimate actually one can prove for A3 and A4, but A2 estimate for A2 is different, because here we cannot use this estimates, kernel estimate directly, because we are actually in this part, and in this part we do not have the kernel estimate, because you only have the asymptotic estimates of this. But one can estimate using again the risk potential estimate. For this, so again here to use this potential, we use we convert this problem into risk potential estimate using Holder's inequality. Because we are in the range q between, so we are in the range q between 1 to 2. So, what we will do, and we are in the A2. So, if you use the Holder's inequality, so this means we are A2 means this set. So, this is x such that 1 minus less than mod x 1 plus this thing, and we are actually here in this side we need L2, and that means we need here basically we need to have, because we are in this range, we can have 2 by q and its Holder conjugate. So, here is be q by 2 and it should be 1 by 1 minus q by 2. I think this is correct. Sorry, this is the measure of this set. Now, again here we are using L2 estimate, we can again convert to the Riesz potential estimate, this operator. So, this operator, okay, first of all, what is this measure of this operator? Sorry, measure of this set. So, measure of this set is actually LQ, because we are in the annulus and LQ is very small and we have this power. And now, up to some constant, we can again using Plancherel can again convert it to Riesz potential estimate. But previously we are using some special B, but here is actually B is actually BP. BP means this n point, n by 2, n plus 1 by 2 by 1 by q. So, we cannot use that estimate, but we can use estimate using this property of the atoms. The estimate that is we have exactly the complement of this part. The complement means the reciprocal of this part. And how to estimate? So, let us at least write some sketch of this. IB pay. So, we will use here that Riesz potential can be write in terms of heat kernel. So, it is defined using B by 2 minus 1 Pt convolution A dt. B by 2 minus 1. So, Riesz potential can be write in terms of this expression with respect to this heat kernel, and if you use the semi-group property of the heat kernel, then actually one can write this L2 norm in B minus 1 times Pt convolution square dx dt up to some constant actually. And next what we will do, we will because this is a, if you take this here, so this is our Rn. If you take this integration here, so we actually there is this is a square of this function. One of that we will take with L infinity norm, and other will take the L1 norm. So basically